Hello and welcome to the video tutorial series about polyhedral computations in Matlab and Octave using bensolve tools. In this video we will be talking about the half-space representation of polyhedra in Matlab. So what is this? Well, a polyhedron is usually defined as the intersection of finitely many half-spaces. So for instance, the polyhedron you see right here is the intersection of four half-spaces corresponding to its so-called facets. The first half-space describing it is this one here, which is generated by the affine inequality -1 less or equal 2x1 plus 1x2. The second one looks like this. The third one is defined by this affine inequality, and this is the last one. Now we can conclude that a polyhedron is the solution set of an affine inequality set. And this inequality set we can write in a vectorized way, like this here. So the lower bounding values form a vector, and the coefficients of the affine inequalities form the so-called coefficient matrix, which is green in this case here. So to generalize this whole setting, we need a lower bounding vector A and the coefficient matrix B. This is the data corresponding to finitely many half spaces, and thus we call this a half-space representation of a polyhedron. Now, how to work with a polyhedron represented in this way in Matlab? Well, what we will do is we will store the matricial data, which means the vector A and the matrix B, as fields of a data structure called rep. And then we will hand this data structure to the package bensolve tools, and we can start working with the polyhedron. Now for you to reproduce the following part of the video, we assume you already installed the toolbox bensolve tools for your Matlab or Octave distribution. If not, we will link you to the video where we describe how to do this, or you should visit bensolve.tools.org. So the first thing we'll want to do is to store the vector 0, 0, -1, -1 as field A of the data structure, which we will call rep. Of course, you can call the data structure as you wish. Now the second step is to store the matrix -1, 1, 1, 1, -2, 1, 2, 1 as field B of the data structure rep. Now we can construct a polyhedral object, which we will call P. We build this up by calling the function polyh, which gets the rep data structure as first argument, and the second argument will be the character h, telling the function that in the rep data structure an h representation is stored. To check our result, we will plot the polyhedron P. To do this, we use the plot function, which is built in the bensolve tools package. You can call the function by p.plot. So this looks exactly like the polyhedron from the first slide, so we did right. Having your polyhedron stored in a data structure, polyh, you can start working with it. For instance, you can start computing the vertices, you can use the polyhedron as feasible region of a linear program, and so on and so on. Well, this worked out fine so far, but what do you do if you have an upper bounded affine inequality? Well, you could just multiply it by -1 and you get a lower bounded affine inequality. But why bother if you can just introduce an upper bounding vector called B to the system? Having both lower and upper bounds available comes in very handy when handling equations. So as an equation can be expressed as two inequalities, we can express this in our framework by setting the lower and upper bounding vector entry corresponding to this affine term to the same value. In this case, it's 4. So the next special case we want to express in our h representation are plain variable bounds like x1 lower equal 3, or even double bounds for variables. So as this does not need any affine term, we will introduce lower bounding vectors L and U for variables. So having all these together, we introduce this more user-friendly h representing system consisting of affine inequalities, which are double bounded by the vectors A and B, and having the coefficient matrix B, and variable bounds L and U. As last part of this video, I will show you how to find out how the polyhedron described by this h representing system looks like using the toolbox bensolve tools. Since the variable bounding vectors have 3 entries, this here is a 3-dimensional example. Now the first thing we want to do is to clear the rep data structure, since we deal with a new polyhedron now. And now we start setting the fields of the new data structure as -12, -12. The matrix B is now -1, 1, 0, 1, 1, 0. Now we got a upper bounding vector for the affine inequalities, which is 12, and 12. We've got a lower bounding vector for the variables, which is minus 6, minus infinity and 0. And this is of course a column vector. And now we've got the upper bounding vector for the variables, which is 6, infinity and 12. So to construct the polyhedron, which we will call R now, we again call the function polyh, give it the rep data structure and tell it that we have an H represented polyhedron. And now we can plot it, and it looks like this. In the following videos, I will show you how to compute the vertices of an H-represented polyhedron, which corresponds to solving the so-called vertex enumeration problem. I will show you how to intersect polyhedra, how to compute the Minkowski sum, and so on. So stay tuned and thank you for watching.